Decision trees. A decision tree is a hierarchical data structure implementing the divide-and-conquer strategy. It is an efficient non-parametric method which can be used for both classification and regression. We discuss learning algorithms that build the tree from a given labeled training sample, as well as how the tree can be converted to a set of simple rules that are easy to understand. Another possibility is to learn a rule base directly. Introduction. In a parametric estimation, we define a model over the whole input space and learn its parameters from all of the training data. Then we use the same model and the same parameter set for any test input. In non-parametric estimation, we divide the input space into local regions defined by a distance measure like the Euclidean norm, and for each input, the corresponding local model computed from the training data in that region is used. In the instance-based models we discussed in Chapter 8, given an input, identifying the local data, defining the local model is costly. It requires calculating the distances from the given input to all of the training instances, which is big O of n. A decision tree is a hierarchical model for supervised learning whereby the local regions is identified in a sequence of recursive splits in a smaller number of steps. A decision tree is composed of internal decision nodes and terminal leaves. See Figure 9.1. Each decision node M implements a test function fm of x with discrete outcomes, labeling the branches. Given an input, at each node, a test is applied, and one of the branches is taken depending on the outcome. This process starts at the root and is repeated recursively until a leaf node is hit, at which point the value written in the leaf constitutes the output. Figure 9.1 example of a dataset and the corresponding decision tree. Oval nodes are the decision nodes, and the rectangles are leaf nodes. The univariate decision node splits along one axis, and the successive splits are orthogonal to each other. After the first bit, the set x, conditioning on x1 less than w10, is pure and is not split further. A decision tree is also a non-parametric model in the sense that we do not assume any parametric form for the class densities, and the tree structure is not fixed a priori, but the tree grows. Branches and leaves are added during learning depending on the complexity of the problem inherent in the data. Each fm of x defines a discriminant in the d-dimensional input space, dividing it into smaller regions that are further subdivided as we take a path from the root down. Fm dot is a simple function, and when written down as a tree, a complex function is broken down into a series of simple decisions. Different decision tree methods assume different methods for Fm dot. In the model, class defines the shape of the discriminant and the shape of regions. Each leaf node has an output label, which in the case of classification is the class code, and in regression is a numerical value. A leaf node defines a localized region in the input space where instances falling in this region have the same labels. In classification, or very similar numerical outputs. In regression, the boundaries of the regions are defined by the discriminants that are coded in the internal nodes on the path, from root to the leaf node. The hierarchical placement of decisions allows a fast localizations of the region covering an input. For example, if the decisions are binary, then in the best case, each decision eliminates half of the cases. If there are B regions, then in the best case, the correct region can be found in log base 2 of B decisions. Another advantage of the decision tree is interpretability. As we will see shortly, the tree can be converted to a set of if-then rules that are easily understandable. For this reason, decision trees are very popular and sometimes preferred over more accurate but less interpretable methods. We started with univariate trees, where the test in a decision node uses only one input variable, and we see how such trees can be constructed. For classification and regression, we later generalize this to multivariate trees where all inputs can be used in an internal node.